I'm the session chair. We have three talks, two of which are by Zoom and one is in person. And the first one is by Horace Smith. He'll be talking about period changes in the evolution of RR Lyrae stars. And I believe we have him all queued up. Horace, are you there?
I am.
Alrighty. Your presentation is ready whenever you are.
Okay. Now, my subject today is now rather a traditional one in the study of these variables. It's been around for a long time, but I do hope to have one little addendum at the end on a subject that perhaps hasn't been commented on quite so long, the evolution of George Preston. If we go back to the early days of awareness that RR Lyrae stars and Cepheids were pulsating, we find that the importance of the period, the pulsation equation was realized by people like author Stanley Eddington. He said the purpose of a Cepheid, the period of a Cepheid variable can be determined with great accuracy. In many cases, it is given in the ephemerides to 7 significant figures. And some of these stars have been observed for more than a century. We can thus discover very small changes of density and so determine, or at least set a limit to, the rate of the progress of the evolution of those stars. And that's still the goal today. A little definition. RR Lyrae stars, of course, almost all have periods smaller than a day. The type 2 Cepheids, there's been a bit of debate over where the division line should be between stars called B-L-Hertz stars and W Virginis stars. Here, let's follow the recent Bono et al. Paper with setting a 5-day limit for the B-L-Hertz stars and going up to 20 days for the W Vir, where they gradually merge into the realm of the Alvi Tori variables. And this paper is, this figure is borrowed from John Percy. And we see the RR Lyrae stars on the horizontal branch. Above them, most of the metal poor B-L-Hertz stars, at least, are believed to be evolving from blue horizontal branch positions across the instability strip toward the asymptotic giant branch, and thus should have increasing periods. For the W Vir stars, some of them will be maybe evolving redwood, some blueward, and whether or not these thermal pulses, blue loops into the instability strip, exist, well, that's a matter of some debate at the moment. So they may or may not contribute to the problem. And finally, we get up to the top of the instability strip in the Alvi Tori realm, and now we're going to be evolving mostly blueward, heading toward the white dwarf stage. So are the observed period changes consistent with the predictions of stellar evolution theory? And we had an introduction to O-C diagrams in the last talk. I'll remind people that if you have a star that's changing in period at a constant rate, and you make an O-C diagram with a single period, you'll end up with a parabolic O-C diagram to a very good approximation. And I'm going to be talking mainly about stars that have been observed for going on a century. Now, the recent work with the OGO survey is going to contribute very much to this study. And as the decades of observation increase, I'm not going to be talking about that for the most part. These will be the old traditional stars that began to be observed back in the days of the Harvard patrol plates. Oh, and my screen is hung up. Here it's going again. Okay. Little computer problem. There. However, let's anthropomorphize our stars. Smiling stars or yellow stars are obedient, follow the predictions of stellar evolution theory. Our bomb-throwing stars are rebellious and don't obey the predictions of stellar evolution theory. So just a brief overview of our stars. Predictions allow both period increases and decreases, but predictions say that in the span of a century, most stars should show evolution in only one direction. That is a period increase or a period decrease, not much of a change at all, but very few stars should show both period increases and decreases in the span of a century due to the progression of nuclear burning. The rates for most stars should be small, up to a few hundredths of a day per million years, maybe getting a little bit larger as we get toward the very end of the horizontal branch lifetime. But nonetheless, even if we have a century of observations, we're looking at only about 1 part in 100,000 or 1 part in a million of perhaps the lifetime of the Aurora star in the instability strip. So we're looking at only a short snapshot in the actual change of the star. This is a plot from a few years ago made by Marcio Catalan. And although the data's changed a little bit since then, the basic picture has, on the y-axis, we have the average rate of period change for Aurora stars in a globular cluster, in days per million years. On the x-axis, we have a measure of horizontal branch color. B, the number of stars to the blue of the instability strip, R, the number to the red, and V, the number of Aurora stars. So -1 is a very red horizontal branch, +1, a very blue horizontal branch, and the solid line is basically a prediction of stellar evolution theory. Now, whether or not the stars at the blue end are really behaving exactly as that uptick in period would suggest may be a little debatable, but overall, in the ensemble, we see that these Aurora stars are following the prediction of stellar evolution theory to within a factor of 1.5 or 2, or some small number like that. But if we look at individual Aurora stars, we see that that need not be the case. This is AR Hercules, a well-known field Aurora star with the Blasco effect. This is its O-C diagram, calculated with a constant period through the 20th and into the 21st century. Only a slow rate of period change for the first half of the 20th century. Then bang, we have an abrupt change in period. The period drops, period goes back up. And then for the last 40 years or so, once again, only a slow rate of period change. But there was clearly some kind of instability in the middle. Same for XC Cygni, another well-known Blasco star, although there are examples of this behavior that are in stars that do not have a strong Blasco effect. Here we have O-C diagram from the 20th into the 21st century. Slow rate of period change. And then around 1960s, a very strong drop in period, followed by an increase in period, and then slow rate of period change again. So there's some kind of instability that took place briefly, whether it was something like the compositional instabilities proposed by Swigert and Renzini back in the 1970s, or something else isn't clear, but obviously something beyond the normal smooth progression of nuclear burning was changing the pulsation period. And if you look at the field stars in the LeBourne et al. Study, again, you'll see the same thing. In the median, the average period change is not far off the prediction of stellar evolution theory. but individual stars can differ by quite a bit. So let's go to the type 2 Cepheids. Let's look at some predictions from the recent Bono et al. Paper. BL Herc stars, mainly increasing periods. W Vir stars, leaving out the gravonuclear loops, more increasing than decreasing, except maybe at the long period tail. RV Tauri stars would have mostly decreasing periods. If we look at the diagram, here are BL Herc stars. Period change, days per million years against period. Not too much to alarm theorists. Increasing periods, just what we expect for stars evolving from the blue to the red through the instability strip. There are a couple BL Herc stars with negative period changes, small negative changes. Actually, those tend to be more metal-rich stars, suggesting that the metal-rich period BL Herc stars may have somewhat different origins or evolutions than the metal-poor ones, which wouldn't be surprising. I've lost my screen saving. Can you hear me? I have lost the connection. I'll try to bring it up again.
We can hear you, Horace. Just you don't have your screen up. That's all.
Yeah, it's the connection seems to have dropped. Trying to get it to share once again. Okay. Sorry about that. I don't know what.
We have your screen up. Just you have to start the slideshow.
Yeah, I'm trying to hit it and it's not responding on the shared screen. Now it's came back oddly showing. Well, we'll pick up from here. I don't know what went wrong with the sharing.
I think it all looks good so far. So go ahead and
Okay.
restart.
Okay. So I was saying that the BL Herc stars seem to be obeying, but when we go to look at the individual BL Herc stars, even there, for example, in V1 and the globular cluster M13, remember a constant rate of period change should show like a parabola. Here we see that although the overall rate of period change matches the predictions of stellar evolution theory, there are actual deviations from a parabolic shape, indicating that there are nonetheless irregularities. If we add the WVER stars to the diagram, well, we see both period increases and decreases, but they're just not enough stars for the pattern to appear as to whether they obey or do not obey stellar evolution theory. And there are, again, erratic stars where we see erratic period changes that must have another origin. Here's one, B1 and M12, where the period has jumped around between 15.5 and 15.55 days without revealing an overall trend over the last century. So quickly go through this. For the Aurora stars in the ensemble, things aren't too bad with the predictions of stellar evolution theory, but the same cannot be said for some individual Aurora stars, where some kind of instability is clearly present. The L-Herc stars, again in the ensemble, obey theory, but even there are irregularities in the period changes of individual stars that must have another cause. And WVER, we don't really know yet whether they obey the predictions of stellar evolution theory, but even there, the erratic stars show that there are difficulties. So I wanted to say, however, make a few comments on the evolution of the honoree of this occasion, George Preston. So I took a look at his papers in the ADS, made a quick summary by decade of the topics of his wide-ranging research. Here we see the number of papers per decade, roughly dealing with Aurora stars and Cepheids is the orange. The chemically peculiar and magnetically interesting stars in the blue. The very metal poor stars in the green, and other topics in the yellow. And looking at this diagram, one thing occurred to me. Here we see the Aurora stars at the beginning, at the end. Is that a trend, or does it mean that George Preston is periodic? We should know the answer to that question before too long. Thank you, and I hope you were able to follow despite the difficulties there.
Thank you, Horace, for an entertaining ending to that talk. Questions in the audience? Okay. Are there, look online, see if there's any questions online here. Oh, Howard, you have a question. Go ahead. Howard Bond.
Hi, would it be possible for me to show a slide?
I can stop sharing here.
Okay, is this showing up?
It's coming up, Howard. Yes, go ahead.
So this is a pair of figures from a paper our group published just a few months ago. We've identified a fairly complete census of stars above the horizontal branch in galactic globular clusters based on both photometry showing large Balmer jumps and then proper motions from Gaia. So these are very pure samples of cluster members. And I'm just showing here M14, a very remarkable globular cluster with a very large number of type 2 Cepheids. The star is here marked with V's, or the type 2 Cepheids. Now, it's been known for quite some time, I believe, that the presence of type 2 Cepheids is strongly associated with very blue horizontal branches, as indeed you see here in M14. So here's the color magnitude diagram on the left, and on the right, I've superposed post-horizontal branch evolutionary tracks from Miller-Bertolami. And you can see that, that the stars here at the extreme blue horizontal branch evolve upwards and then to the right across the HR diagram. And indeed, in M14, you see not only the Cepheids, but there's a clear sequence of blue above horizontal branch stars, which you can see here. And so our interpretation is that, first of all, quite a few of the RR Lyraes are actually originated on the blue horizontal branch and are evolving across here. That's also true of the BL Hurst stars slightly above the horizontal branch. And even most of the type 2 Cepheids originated way down on the blue horizontal branch and are evolving to the right. So we would expect most of them to have increasing pulsation periods, which I think agrees largely with what you were saying.
Well,
There
for
would
the
be-
BL Herc stars, that's true. They all mostly have increasing periods, but the pattern is not clear for the W verse stars.
Well, that's right, but
Yeah.
I think most of them do have increasing pulsation periods. Now, there are these various loops and so forth. A few could have decreasing periods, and then at the bright end, then they're evolving back, to the top of the white dwarf cooling track, and they would have decreasing periods. But we expect the bulk of the type 2 Cepheids to have increasing periods as they evolve to the right.
And that would certainly be in agreement with the Giuseppe's predictions as well. And but I think for the W ver, I think we may need more data to say whether the observations agree with that prediction.
Oh, absolutely.
All right, thank you very much for sharing that, Howard. Any questions from the audience? We're pretty much at the end of Horace's time slots. Let's thank Horace Smith and Howard one more time. All right, our next speaker is Barry Medor, in-person talk, unifying Sturge's law, Bailey types, and Osterhoff groups.